Hello there. In this video we're going to talk about a basic concept that is going to be used in the next coming videos, and that is called the degrees of freedom. So the definition of degrees of freedom has various definitions depending on the approach you're pretty much going at it from, but in general it's the number of, or the minimum number of coordinates or values that can specify a position in a system or calculation completely. And let me just go through about 4 examples to sort of illustrate this idea. So one basic concept of degrees of freedom that most people are already familiar with is spatial coordinates. So let us consider R2, or two-dimensional space. So typically we can represent this as x versus y. So if I have any point in xy space, or R2, I can usually represent it with two numbers of some sorts, right? So I can uniquely determine any point in R2 via an x-coordinate and a corresponding y-coordinate. Now this is not the only way to specify location in R2. Instead we can use a system known as polar coordinates, which is pretty much a circular way of representing spaces. So for example, if I want to say identify that point, then that's going to have a radius of 3 and an angle of say pi divided by 4. So I can correspond this point by 3 comma pi over 4 in the r comma theta perspective. Now of course these are equivalent systems, there's mapping back and forth, but nonetheless there's at least 2 numbers that must uniquely specify a point in R2. So that means the degrees of freedom equals 2. And sometimes we're going to represent this by Greek letter nu, which looks like a Greek letter V. But if you ever hear me say nu, I'm talking about this Greek letter. Looks like it kind of like a bird. Here's a more hands-on example. So suppose there are 4 different types of food, or 4 different dishes to choose from. And 4 people must select one dish. And there's only one of each dish available. So I'm going to call it food 1, food 2, food 3, and food 4. And we have 4 different people to sort of select a dish. I'm going to call it person 1, person 2, person 3, and person 4. Alright, so let's start with person 1 because we're not really identifying these uniquely. So person 1 has the option of choosing food 1, food 2, food 3, or food 4, and it doesn't matter which one he picks. So let us assume he picks food 1. So that means food 1 is gone. So at this stage we have food 2, food 3, and food 4 remaining. And then we have person 2, person 3, and person 4 that need to select a food. So let's start with person 2 because it doesn't really matter. Person 2 can choose either one of 2, 3, or 4. And let us assume without loss of generality that he chooses food 2. Continuing in this fashion, that means we have food 3 and food 4 left, and person 3 and person 4 to choose. So let's assume person 3 chooses next, so he could choose either 3 or 4. And let's assume without loss of generality he chooses 3. So that means what? That means we have food 4 and person 4. Notice there is no choice that person 4 needs to make because he automatically gets food 4 by default. So that means what? That means person 4 has no choice. So that means only 3 people, namely person 3, person 2, and person 1, had a freedom to choose, whereas person 4 did not. So that means only 3 of the 4 had a freedom of choice. So that means there are 3 degrees of freedom in this system, which we will write nu is equal to 3. And from the initial case, that means 4 minus 1. So if we generalize this to, say, food 1, food 2, down to food n, and we had person 1, person 2, down to person n. So technically, person 1 could choose that one, person 2 could choose that one, and person n minus 1 can choose the one before it. But this one is going to have no freedom of choice at all. So that means nu is going to be equal to n minus 1. So let's take another example. Suppose we have one sample, S, of size n. And let us assume this n value is fixed. So once you choose one, you cannot change it. So if we wanted to calculate the sample mean, x bar is going to be equal to the summation of x divided by n. And if we rearrange this equation, that means the sum of the x values must be equal to the mean times the number we have. So if this value is going to be fixed, the set in an arbitrary way, and n is going to be fixed, that means x bar is also going to be fixed as well. So this right-hand side is going to be a fixed constant. So let's say it's equal to, 35. So how many degrees of freedom for the values in my sample do we have? So recall that the sample is consisting of values x1, x2, all the way down to xm minus 1, comma, xm. So how many degrees of freedom do we have in these values if we want a particular x bar and m? Well, if you think about it this way, I can choose any values for x1 through xm minus 1. It doesn't really matter. So that means let us assume, for example, x1, x2 down to, say, xm minus 1, and I add them all up. Let us assume that value is equal to 20. And let us assume that, n is equal to, say, 10. So if that is true, then that means 20 plus the last value must be equal to the mean, which is 35, times 10. Now notice xn does not have any freedom because there is a unique solution that makes this true. So that means xn does not have a freedom to be anything they want. Whereas, you can rearrange xn through xn plus 1 to be any values. As long as that number is equal to 20, it doesn't matter what those values are. So that means there are n minus 1 degrees of freedom for one sample of size n. Which means nu, again, is equal to n minus 1. And we're going to use this conclusion later, but always, for one sample of size n, the degrees of freedom is n minus 1. And let's take another example to just illustrate this idea. So consider the following contingency table. Let us consider genders, say male and female. And let us consider the classifications of smoking. So let us assume they do not smoke. Let us assume they are a moderate smoker. And let's assume that they are a heavy smoker. And let's assume this is an exhaustive set, so there are no other possible values here. So let us assume there are some values that are associated with this. And let us talk about how many degrees of freedom are there. So we have two categories for gender. So let us assume a person, X, has a particular gender, So if we assign it to be equal to male, then there's no degrees of freedom in order to be a female, right? And vice versa, if X is a female, there is no freedom to change into a male under standard scenarios. So for gender, there is going to be 2 minus 1 degrees of freedom. Whereas this case, for example, I can choose that or that, but if I choose one of these two, then that does not give me freedom to have any choice to be in the third category. So there's going to be 3 minus 1 degrees of freedom for the classification area. And since we're in two dimensionals here, we can multiply these degrees of freedom together. So the degrees of freedom is going to be equal to the degrees of freedom for the gender times the degrees of freedom for the classification, which is going to be equal to 1 times 2, which is 2. So that means the degrees of freedom for this contingency table is equal to 2. And if you don't really want to go into the understanding of why we want this to be true, typically for a contingency table, this is going to be equal to the number of rows minus 1 times the number of columns minus 1. There are some exceptions, but this is typically the rule that people follow, unless there's something else that's being considered here. And that's pretty much a quick breakdown of degrees of freedom. Most of the time you do not need a full, deep understanding of what degrees of freedom represents, but at least know how to identify how many degrees of freedom are in a system, or a calculation, or a sample, given some constraints.